You can hold on to it till Friday if you want. Oh, you're not going to be here? I'll take it.
Oh, that's true.
Oh, okay.
Thanks for making sense.
I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. Help us to glorify you in what we do. In your name I pray, Lord Jesus. Amen. So we have a visitor today. This is my son, Matthew.
Hey, Matthew. Hey, Matthew.
Yes. He'll be doing his schoolwork over there. All you got to use.
He's not doing calculus?
Calculus 3.
No calculus for Matthew today. In fact, he left his math homework at home. So, yeah. All right. So let's see here. Where'd it go? Well, all right. Well, I've got all the papers except the one I want.
No.
Did you forget your math homework at home too?
Oh, here it is. All right, so let me get to it. This is the ratio test. So consider the sum, a sub k, k equals n naught to infinity. All right, such that a sub k is not equal to 0 for k sufficiently large. Now I don't think I've stated the theorem quite this robustly in the notes. Like I've given you kind of a less toned down version of this, but you could say it this way. I guess I'll just say it the way I say it. Let k naught for k greater than, forget the sufficiently large. Let's just say greater than or equal to n naught. There we go. All right. Let rho equal to the limit as k goes to infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k. All right. All right. And I won't even I'm not going to state the conclusions of the ratio test just now. I want to try to derive them for you at the moment, all right? So let's try to work through that. So there are basically going to be two cases. So suppose rho is less than 1. All right. So we can analyze what would happen if the limit of that quotient exists and it's less than 1. If that's the case, right, then there exists r greater than 0 such that what? I mean, I don't even really need to say it's greater than 0, but you can put an r between rho and 1, right? I mean, think about that. If rho is less than 1, then I can definitely find a number between rho and 1, right? I could be more specific if you'd like, right? Take the average of 1 and rho, right? Halfway between it, there's the number you're looking for if you want. But I'm not insisting it be that. Okay, then what? Well, then notice that we have the limit, this limit exists, right? What does that mean? That means that we can make, the absolute value of a sub k plus 1 over the absolute value of a sub k, right? Minus rho. We can make the absolute value of that as small as we like, right? And how small would we like it to be? Well, let's see here. What's a convenient thing which is, positive? Well, how about if we take r minus rho? In other words, I'm saying, all right, so let me finish my sentence here. Observe r minus rho is positive, and choose, let's say n, in the natural numbers such that little k greater than or equal to n implies this, all right? let me draw an arrow of thinking. So I'm saying this, and then, sorry, bad formatting on my part, implies that, okay? Great, then what? Well, what does this mean? Whenever you have an absolute value inequality, you get two things, right? You get minus this number below it, and you get that number above it. So let me just get the one that's interesting. We get ak plus 1, the absolute value of ak plus 1 over the absolute value of ak minus rho is less than r minus rho. All right, so then what? Well, if we do what? Just add rho to both sides, right? What do you get then? Adding rho to both sides, we get the absolute value of ak plus 1 divided by the absolute value of ak is less than r. Well, this is interesting, right? This is interesting because if you look at this then, we can reformulate this to say what? You've got absolute value of ak plus 1 is less than r times the absolute value of ak, right? And then what? So whenever we come up in this class about, when we come to something like this, some kind of general relation between, you know, one order and a next, a good next move is to start looking at how it behaves for, say, k equals 1, k equals 2, k equals 3. Like, what's the relation here, you know? So if I look at k equals to 1, what do I get? I get the absolute value of a2 is less than r times the absolute value of a1, right? Fine, that's k equals 2. What happens with k equals 3? Excuse me, this is k equals 1. K equals 2, what happens? Absolute value of a3 is less than r times the absolute value of a2, right? But what did we just learn the step above? That's less than r times the absolute value of a1, right? So this is less than r squared times the absolute value of a1. All right, maybe there's going to be a pattern we're going to find here. What happens with k equals to 3? Absolute value of a4 less than r times the absolute value of a3, right? But we just learned that the absolute value of a3 is less than r squared times the absolute value of a1. So fold that in. What do you got? You got r cubed times the absolute value of a1. Can you see the pattern? What's the rule for, let's say, k equals to j? If I put k equals to j, what do you see there? If we look at the jth one, we have the absolute value of aj plus 1, right? Or, I mean, I guess I could put j minus 1 to be more interesting. J minus 1. Then that would give me absolute value of aj is less than what? R times, well, r to the what? Let's get to the point. R to the j minus 1, right? Times the absolute value of a1. That's the pattern here, right? So what does this allow us to do? So if you look at it then, we've got the sum, let's see here. Let me just get straight to the point. We can compare the absolute value of the series, right? We can compare the series of absolute values, right? Summing together the absolute values of the series. Let me just write it this way. So what we find then is that the sum of the absolute value of aj, right? Let's say j equals n naught to n, right? Is going to be less than what? The sum j equals n naught to n of r to the j minus 1, absolute value of aj, right? A1, right? Now the absolute value of A1 is just a constant, right? So can you guys tell me what this proves? What kind of series are we looking at over here? Let me, one more step and maybe it'll make it obvious. So absolute value of A1 times the sum r to the j minus 1, j equals n naught to n. So That's a convergent series. Why? If you let n go to infinity, rather, that's convergent. I mean, that sequence of partial sums converges. What is this, the sequence of partial sums for? Yeah, the geometric series, right. This is a geometric series with ratio what? R less than 1. Therefore, that converges. Consequently, by the direct comparison test, the absolute value of the given series converges, which goes to show you that the given series, right, is in fact absolutely convergent. So if the ratio rho works out to be less than 1, this argument proves that the series is absolutely convergent. Now, what if the rho is greater than 1? What would happen then? How would that go? So if rho is greater than 1, then what you can do is 1 is less than r is less than rho, right? If your rho for the ratio test is larger than 1, then you can fit a ratio between 1 and the rho, right? And in that case, you'd have rho minus r is positive, and then you'd exploit the other side of the inequality. Anyway, so if that's the case, then you can basically, the argument essentially goes through the same. It's just now you can compare to a geometric series, which is in fact smaller than the, well, not even a geometric series. You can compare to a series, okay, fine, it's geometric, but it's a divergent geometric series, which is smaller than the given series. So in the case that rho is greater than 1, essentially the same argument shows you that it diverges. All right? And that's the ratio test. Yep.
What if rho is 1?
Ah, interesting question. So let's look at that. Oh, sorry. Does that get it now? Is that where you're looking? Are we got it? No? Oh well. Do I need to put it back up? No? Okay. Sorry. You know, we used to have these like on a cord that you could just pull. It was simpler times. Let's see here. So you're asking, what if rho equals to 1? Well, check this out. How about this? If we look at the series k equals 1 to infinity of k, all right? Then what's the absolute value of ak plus 1 over k plus 1 over a sub k? Well, it's literally k plus 1 over k, right? And this goes to what? I mean, fine, I've been showing this step, so let me continue. 1 plus 1 over k, right? I mean, fine. Why am I making this more complicated than it needs to be? That's just 1 plus 1 over k, right? What happens to that as k goes to infinity? That goes to 1, right? So this series is? Oh! Oh! You hurt me with that. No, this series is not convergent. This is k, like you're adding up 1 plus 2 plus 3 plus, this blows up very badly. Like a lot. No, this is very divergent. So, okay, so the radius, the rho could be 1 for a divergent series, right? All right, let's try something else. Example 2, my favorite, the p equals 2 series. We know that converges, right? This guy. In fact, Euler proved it's pi squared over 6. Hooray. But so not only does it converge, I know the value. Not that I proved it, but if I say it twice, it makes it true, right? Calculate L for this. So I've got 1 over k plus 1 quantity squared, right? Divided by 1 over k squared, which is, of course, k squared over k plus 1 squared, which you can simplify to 1 over 1 plus 1 over k, quantity squared, which goes to 1, as k goes to infinity. I divided the top and the bottom by k squared, but when you bring the k inside the square, it becomes a squared. Or wait a minute, the other way around. Divide the top and bottom by k squared. Oh yeah, when you bring the k squared inside the thing, it becomes 1 over k. Anyway, this you can check the algebra on if you like, however you want to. It works out to 1. So what's my point? This is convergent, right? This one, divergent, right? They're both rho equals to 1. So what do we get to say when rho equals to 1? Nothing. You can't say anything. It's inconclusive. It's like when the limit of a sub k is 0. That does not give you the right to say the series converges. Far from it, right? That just means you must consult other physicians, get a second opinion, you know. Although I don't really trust doctors anymore. But anyway, my parents are doctors. I'm allowed to say that. Let's see here. So there's that. Now, let me show you guys the other one. The other remaining test, and we'll work problems on this in just so let me get this out of my system here. Then we can work our problems. So this is the root test. The root test says you let L be the limit as k goes to infinity of the kth root of the absolute value of a sub k. All right? And if L is less than 1, it converges absolutely. If L is greater than 1, it diverges. And the proof actually is very similar to the one I just went over. The proof, again, involves looking at what it means for the limit to exist, and from that, extracting a radius for a geometric series with which you can compare the given series. It's literally the same. It's almost the same proof, really. So I won't write it out. I'll just talk through it here. So if this limit exists and L is less than 1, then you can pick an R between L and 1, right? Which then means that R minus L is a positive number. So that means that we can pick M sufficiently large so that k beyond that M makes the absolute value of the kth root of the absolute value of a sub k minus L. That distance has to be less than that epsilon, which I'm choosing to be R minus L. But then that gives me that the kth root minus L is less than R minus L. Adding L to both sides gives us an estimate for the size of the kth root of the absolute value of a sub k being less than R, which then straight away allows me to compare to the geometric series with the radius R less than 1, which converges. Therefore, by direct comparison test, if L is less than 1, the series converges. And not just converges, it actually converges absolutely. And then the proof for L greater than 1 is very similar. You pick an R between 1 and L. That allows you to create an epsilon in the form L minus R greater than 0. Again, you can pick M sufficiently large to make the absolute value of the kth root to be less than that epsilon, in this case L minus R. This time I exploit the inequality on the other side. See, instead of doing less than L minus R, I do greater than R minus L. Like that's the other half of this absolute value being less than a number, right? Absolute value being less than a number gives you two things, one side and the other, right? It gives you a compound inequality. Here's the other side of it. And since I get that, I can add L to both sides, and then I get the radius is in fact less than the kth root in this case. But then that means that you have a geometric series with radius larger than 1 that blows up, right? And it's smaller than your given series, therefore your series diverges. So, because it ends up showing that it's unbounded. So, so basically the case 2 is by the kth term test. But anyway. So I'm going to put this away and write examples out for you guys, all right? Any questions? Yeah.
If L is equal to 1, guessing we don't know.
If L equals to 1. Let's see here. Do I have an example already on tap? No, I don't. How about, let's see here. What's, for what?
450 instead of, maybe I was looking wrong.
You're probably not. Which one was it? 450? Oh man. Oh, well, okay, yeah. I mean, um, good point. Yes, this is part of it. So this example shows that if the radius is 1, it could be divergent, right? And this is an interesting example, I suppose, because it's the thing I haven't talked about in class yet, which is a limit of the type 1 to, let's see here. Well, this one down here is 1 to the infinity, you know. This indeterminate 1 to infinity works out to e. I worked that out back in example 1.34, which I have not covered in class. But it's the one thing in sequences that I didn't cover in class. So let's see here. So that's divergent. I'm trying to think if you come up with an example which would not be. I mean, I know that the ratio test working out to 1 is inconclusive as well. I don't know if I have an example of a convergent one on tap to show you that it, you know, it could be convergent. I'm trying to think. Goodness. I can't come up with it off the top of my head. I'm sorry, guys. It is nevertheless inconclusive, and so, but you know, so there are books that have this as a third case in the ratio test, and also the root test. Like case 3, L equals 1 or rho equals 1, nothing happens. But I don't. That's weird to me that you'd put that in the theorem because, like, I don't know. We have theorems all the time that only apply to what they talk about, and we don't also put in the theorem all the things they don't talk about, right? It's just understood. That's the theorem. That's what it says, right? You apply it. And the theorem is silent on rho equals to 1. It doesn't have anything to say, you know? So I don't know. I mean, you could add, you know, if it's equal to 1, you don't get to say anything, but how does that add to the discussion? I mean, I don't know. I mean, I guess it's just saying, hey, if it's, you know, it's like when I write the kth term test, I don't also include a sentence which says, and in the case that the limit is k goes to infinity of a sub k equals to 0, this theorem says nothing. Because it begs the question, so are you saying something? Because you're saying it says, I don't know, but I just say if the limit as k goes to infinity of a sub k is not equal to 0, it implies it diverges, right? That's the kth term test. So I don't know. Let me not go down this road. So despite your fears, this is not a quiz that I have up here. So what I have for you guys is a page which has all of the divergence and convergence tests on them. So this is a page that is a summary of every last convergence divergence theorem except for the one that kind of doesn't matter. That what's that?
Want me to hand them out for you?
No, I got it. I mean, I think I'll be okay. So, yeah, if I hand too many to a row, go to the next row, obviously. So I have this. This is basically just a summary of all the tests, starting with the kth term test, the geometric series, adding and multiplying series,
We were short. Can I get one?
integral test. Sorry, integral test. You know, p-series, tail wags the series. I gave it a name. Direct comparison test, limit comparison test, absolute convergence implies convergence, alternating series test, ratio test, root test. This is it.
Absolutely beautiful.
Can you use it on the test? No.
Worth a shot.
Oh, what if you like if you don't use it, you get bonus points, and if you have to use it, you like.
Let's not go down that path. Because I would like to be able to put a question on the next test, which is like, I don't know, state the root test. You know?
Is it a hint, hint, wink, winks?
Oh, you did give us that the other day. Yeah.
So this here is
Awesome.
not the, oh my goodness. I mean, so are you doing anything else this week?
Yeah.
Because that's all you'd be doing if this was the quiz.
Heck no. Good Lord Almighty.
So, mathematicians are weird. They're like only happy if they have problems, right? So, if this doesn't make you happy, well, I guess you're... No, that's not true. You might still be a mathematician. I don't know. These are just examples. No, this is not an assignment. This is for the sake of discussion. So rather than me making up problems off the top of my head, I have a list of 50 of them to choose from. So these are all jumbled up and mixed up together too. They're sometimes they're nth term tests, sometimes they're geometric series, sometimes they're alternating, sometimes they're root test problems, sometimes they're limit comparison, sometimes they're a combination of methods. Like this is not in the order of the chapter or anything. This is how problems come to you on my test, right? My test doesn't say, here's a series, use the limit comparison test. Here's a series, use the geometric test. It's a problem. You have to decide what's the right tool for the job. Usually. Now, on occasion, I have pity on the students and I say something like, use the integral test to prove this. You know.
You should have more pity, so.
Although that's actually not pity, that's just forcing you to use the integral test. It might be that the limit comparison would be easier. So, yeah, sorry. Spoke too soon. But I know. Well, it's my sneaky way of testing integration on test 2. Yeah. Well, I already got differential equations, right? But anyway, yeah.
There's that these problems say to calculate the sum, but what are you calculating sums on the test or just getting
Oh, yes, we do calculate sums on the test as well, especially if they're geometric or telescoping, right? And if I'm feeling particularly malevolent, I could, you know, give you one that's a Riemann sum. But I said that would be kind of bonus, right? All right, so let me begin the examples. let me put this away unless we should work them out by hand, yeah? All right. I'll start with the ones that I already have typed out. Let's see here. All right, let's see here. I will find it. Oh, here they are. Duh. Here we go. Example, I guess it's example 3. Here we've got the sum k equals 0 to infinity minus 3 to the k. This is not on the list of 50 problems. Don't worry, if you're trying to find it. I mean, if it is, it's coincidental. Okay, so you look at this problem, it's a converge or diverge, all right? So what, yeah. Oh, you had a, what do you guys think we should do? Go to lunch.
I like that idea.
For me, this one, there are 2 options. I think they'll be equally easy. The one option would be to use the alternating series test. This is pretty clearly an alternating series which converges, right? Because this is what? You put in 0, you get 1, and then minus 3 over 3 over 1, right? And then plus 9 over 2 plus 27, well, minus 27 over 6 plus 81 over, well, I don't know, maybe it's not so obvious that it's converging, is it? Let's see here, 24, yeah. Now, eventually the denominator is going to win, right? Because you've got k factorial there, but so it's, look, to do the alternating series test, I would actually have to think a little bit to prove that those terms are eventually decreasing, right? So let's be lazy. Let's use the ratio test instead. So let's use ratio test to avoid thinking. And so the ratio test here would be what? Limit as k goes to infinity of what? We've got the absolute value of minus 3 to the power k divided by, oh, k plus 1, right? Divided by k plus 1 factorial. I regret my font choice here. I'll fix it in a second. Minus 3 to the k divided by k factorial. Absolute value of all that, right? What happens to the minus 3 as the absolute value hits it? What does it do? The absolute value will just erase the minus, right? So this will simplify. This will simplify simply to 3 to the k plus 1 times k factorial divided by 3 to the k times k plus 1 factorial. All right? And if I were you guys, well, I don't know, if I like, sometimes when I'm in a hurry, I would actually go straight to that expression. Once you understand what's going on, like the need to write the thing above it, I don't know. Well, see, if you guys don't write stuff down, you make mistakes, and I'm probably making a mistake right now since I'm talking about making a mistake. It's just like a rule, but hopefully not. What's my next step? Right. Okay, so you're like, I do 3 times 3 to the k times k factorial, and then I'll do what you said, which was factor out, right? Definition of k factorial, k plus 1, right? Factorial was just k plus 1 times k factorial, right? So what happens? See the k factorials, they cancel, right? The 3 to the k's, they cancel. And you're left with what? The limit as k goes to infinity of 3 over k plus 1. Which is what? 0, right? So what does the ratio test say? I'm going to give this a name. I'll call it Jane. Thus, Jane converges. By ratio test. Rho equals to 0, which is, of course, less than 1, right? In fact, this is, by the way, the smallest that rho can work out to, right? Rho will never limit to a negative number. You see why? You're taking the limit of the absolute value of things. So like this is the smallest rho gets, rather. So there you go. Now, you could have worked this as an alternating series, right? But then I would have had to, fuss a little bit to show that the terms are decreasing eventually. Eventually the terms are decreasing, right? For the start, the 3 to the power is winning, isn't it? So another example. Example 4. Suppose we're up against the sum k equals 0 to infinity of k to the k over k factorial. All right. Now, I guess, I don't know, so I don't want to talk about 0 to 0. Let's just go 1 to infinity, just to avoid a discussion there. So then, okay, so you see this problem. This pretty much yells at me, use the ratio test. Like you've got a factorial, and you've also got something that's growing like mad. K to the k is big, right? So like definitely the ratio test is the way to go here. So let's look at that. So what I'm going to do is I'm going to call this a sub k, all right? Fine. And rather than writing the limit at the start, I'm just going to calculate the thing we're taking the limit of in order to save a bunch of writing. So ak plus 1 over a sub k, right? That's what I'm interested in. And of course the absolute value, right? But is the absolute value really a thing here? I mean, this is a positive series, right? So absolute value is kind of a yay, nothing kind of happened. So we have, getting to the point here, k plus 1 to the k plus 1 power, right? Divided by k plus 1 factorial. That's my a sub k, right? And then to divide is to multiply by the reciprocal, right? So to multiply by the reciprocal here, I just multiply by what? Yeah, k factorial divided by k to the k, if that's okay. I'm sorry. No, no apologies. No apologies. Let's see here. So then that is equal to k plus 1 times k plus 1 to the k times k factorial divided by k plus 1 times k factorial times k to the k. Using, well, algebra. Definition of the factorial. Now some things cancel, right? Do you guys see what cancels? There's just like k plus 1 factor here and here. That cancels. That's nice. And this factorial cancels with that factorial. And what's it leave us with? Leaves us with k plus 1 to the k, right? Divided by k to the k. Oh, hey, we can simplify that, right? When you have the same power in a fraction above and below, then we can combine it into a single fraction to that same power, right? So by the laws of algebra, this is the same as k plus 1 over k to the k. And that we can simplify further, right? How's that simplify? 1 plus 1 over k to the k. So at this point, I don't know how much you remember from Calculus 1. I don't know if you've actually read the notes that I've typed up or not, you know, because after all, I posted them, but maybe you've been waiting till I'm done posting it. Whatever, I understand. Let's work through it. How's this limit work? What is the limit as k goes to infinity of, 1 plus 1 over k to the k? What's that equal to? So the way I do this limit is I use the exponential and the natural log together on it. So this is really the limit as k goes to infinity of the exponential of the natural log of the expression I'm up against. So that's just an identity. I can take the exponential of the natural log of a positive quantity. And that's in my favor because this is an indeterminate form that we've not been up against before in class this semester, I don't think. This is type 1 to the infinity. Type 1, this is an indeterminate form. How do you deal with an indeterminate power? The way I deal with it, at least, is I use exponential and log to turn it into, instead of an indeterminate power. Well, let's see what happens here. So, continuing here, using the continuity of the, the exponential, I can pass that limit inside. I can pass the limit inside using continuity of the exponential, and then using properties of the natural log, I bring the k down, and I've got natural log of 1 plus 1 over k, right? So this is a step in the right direction, see, because I've traded type 1 to the infinity instead now to what? This is what type is this? Yeah, infinity times 0, right? So I've traded an indeterminate power for an indeterminate product. So we're closer to using L'Hopital's rule, right? If we want to think about extending k continuously here, of course. And so one more step, this is the exponential of the limit as k goes to infinity of the natural log of 1 plus 1 over k divided by 1 over k. See, that's the next trick here in our arsenal. Now I've converted it to type 0 over 0, right? Now it's type 0 over 0. And so now that it's type 0 over 0, so I can apply L'Hopital's rule, extending k continuously, all right? And what do I get? Differentiate the natural log, I get what? 1 over 1 plus 1 over k, right? Times the derivative of 1 over k, which is what? Minus 1 over k squared, right? So there's my numerator's derivative. How about my denominator's derivative? What's the derivative of 1 over k? Well, minus 1 over k squared, right? So what happens then? You get a minus 1 over k squared upstairs and downstairs. They cancel. What are you left with? You're left with the exponential of just this piece right here. I'll circle it in green. All that remains after you cancel these two guys, it just leaves you with this, right? That limits to what? 1. So we get exponential of 1, also known as e. So in fact, this mysterious limit we're looking at, the limit of it is e. So does the series converge or diverge? It is so important, you guys, to separate the question of the convergence of the sequence you're looking at for the test versus the convergence of the original series. You've got to divorce these in your mind. This is the poison that will kill you on the test. We're talking about convergence of this quotient as a sequence, right? That converges to e. That is a separate question from does this series converge or not, right? There you're asking, does the sequence of partial sums converge? I use the word converge for both, right? But they're logically distinct things. You've got to rip those apart in your mind. That's the fundamental confusion that you're battling as you start studying this material. Everyone does. So what was our, well, you guys got the sheet. It diverges, right? So this is, of course, greater than 1, so therefore S diverges. I'm calling this S to give it a name. Example 5. What if we have the sum n equals 1 to infinity, all right, of, I don't know, n factorial over n to the n. How's that going to go? So here, if you look at a sub n plus 1 over a sub n, because we've got n instead of k, right? That is equal to what? 1 over n to the n over n factorial, right? And what does that go to? My bad. I'm not doing it right. I said it wrong. It's, well, let me not write more. What does this go to? Let me not write anymore. What does this go to? How is this related to my last example? I changed the letter. Can you not see it? This is the term-by-term reciprocal of the previous series, right? So by the same mathematics we just did, this will go to 1 over e, which of course is less than 1. So therefore, converges by ratio test. So does it matter if you put the AK plus 1 upstairs or downstairs? It matters a lot, right? It will turn your answer upside down, see, because to each divergent example, there exists a corresponding convergent example, and vice versa, yeah.
But it's the same process either way to get to.
Yeah, I mean, if the algebra is just reciprocal, so it's like the same formula, just it flips over. So, example 6. All right, let's suppose we've got the sum n equals 1 to infinity, all right, of, oh, I don't know, let me think about this. The inverse tangent of n plus 3 raised to the n power. Matthew? What do you think about this one? What? What do you think about that one? What do you think about this one?
That's how we built it.
It what? Divergent? He says divergent. What do you guys think? Is he right? I think he's right. I think he's right. See, if Matthew can do it, you guys can do it, right? How old are you, Matthew? How old are you? 9. A 9-year-old can do it. Surely you guys can do it, right? There are sort of two obvious avenues here to show that this is, in fact, divergent. I'm going to do the kind of stupid way, which is to use anytime you have like blah to the n, root test is sometimes a useful thing. That's wasteful here. We could just do the nth term test, right? The nth term test shows if you apply the n, take the limit of the nth term here, it's basically going to pi over 2 to the n power. What happens to that? That blows up. That's infinite, right? But we could also do the root test. So here's my a sub n, right? And so the nth root of the value of an, what is it? It's the nth root of inverse tangent of n plus 3 to the power n. But of course, the nth root function and the nth power function, they're natural enemies. And so when they meet in the wild, they annihilate in a cloud of blood mist. Let's see here. I'm sorry, too violent. But let's see here. So then that just leaves you inverse tangent of n plus 3. What happens to that as n goes to infinity? This goes to what? Pi over 2, which is what? Greater than 1. So therefore, series diverges by what? By root test. Yes. So I wouldn't say that the root test is especially impressive in the divergent case. And I wouldn't say that the ratio test is especially impressive in the divergent case. Really, the shining point is when we can apply it to convergent series. And also, as a rule, if you would try to apply the ratio test to the easiest examples we have, it's inconclusive. So like if you do it to p-series, it's inconclusive. If you do it to things that you could do, direct limit comparisons to the p-series, it'll tend to be inconclusive. So, each one of these tests has their place. But anyway, all of tomorrow is yours. Like tomorrow, you guys can ask me questions about whatever. We got a whole day tomorrow to work on your homework together, and/or to just carve through these questions. All right. So, like plan. And what's Friday? I believe it is math battle, and you've got to turn in your homework. So there's that. But yep.